Okay, thank you. Thank you very much, Bernard. Thank you, Henning. Thank you for all the organizers for having me here. It's a really great pleasure. It's a great setup. So what I'd like to do this morning, you have all recovered from the hack yesterday, so is going in the quantification aspect of proteomics. And the actual title on the program was quantification of proteins. I will focus more on the quantification of peptides, and as John has described it yesterday, right, there is an issue, or the link from peptide to proteins actually quite a challenge, and this is one of the points we may also want to address. But most of the material I'll discuss this morning is actually quantifying peptides, and then we have to do the link back to the protein. What I'll cover in the next 90 minutes also is more or less the basic of quantification. Some are really basic, so if you know it, you can take a short nap. And then for the much more technical stuff and the details, how we actually do the quantification, we have a workshop where we can discuss some of the details. So what I'd like to do is, first of all, to go to a few very general principles in the introductions, then briefly discuss the different way of doing quantification, because there's a number of methods, a number of instruments. So you can have almost any combination of sample preparation, acquisition method, instrument type, and that gives you a wide variety. So I cannot discuss any of those in details, but I try to just more show the general principle and the benefits and limitations of the different strategy. And then quantification at present time is still best done by targeted methods. So I'll focus on the selected reaction monitoring, which is a kind of the gold standard. It also has some limitations, and there is a second generation of targeted approach, which are based on high resolution accurate mass instrument. And I'll try to say some words on that as well. So for introduction and quantification by mass spectrometry, in principle, it's a very simple thing. This is just an example. If you have a spectra, you have, for instance, done a labeled experiment with a heavy and light marker. So you basically, in your spectra, will see isotope patterns corresponding to your endogenous peptide or the light version of it. If you have added an interstandard or heavy version of the label, you get those. And typically what is done, you look at the ratio and you use that as a quantification. That is, in principle, easy to do. However, in practice, things are a little bit more tricky in that first, for example, this one is a short list. We have here a much longer list of things which can be happening in the background. First of all, a peak might not just be a peak. What you see could be the convolution of the peptide you want to quantify, plus some other analytes which are coeluting. And we're dealing with peptide, we're dealing with very complex mixture. We always have more than one component on a column when we separate it. Secondly, what we can do quite well is quantify peptides ending an internal standard at the end, and you can run it 3 times on your LCMS, and you get a CV of 5 or 6 or 10%, and people are very happy. But that doesn't mean that you have a precise quantification of proteins, because there's a many steps before, and usually all these steps have big losses. So you can quantify very precisely your peptides, but this will only represent 10% of your actual protein population if you have a complex workflow. So this is another issue. You need to know or have a handle on the recovery of your entire process, and not just on the analytical step at the end where you quantify your peptides. And there are many other points we need to go through as we move forward. So I think there's nothing new on this slide. Just to put it in perspective, we're doing proteomics, and we have a number of challenges. First is the complexity of the proteome. We have been through that already. We're working in shotgun at the peptide level. So if we start with a proteome, let's say 20,000 proteins, we digest them, you do all the math, but means you have something like 500,000 to millions of different species you have to separate. And you have different ways of separating them. Michael has discussed that yesterday. You can use different chromatography or separation techniques. However, if you use a classical LCMS system, so analytical system, usually the peak capacity, which was explained to you yesterday, of your system is at least by 1 or 2 orders of magnitude off, but the complexity compared to the complexity of your samples. And it's typically, just to give you an example here, you can get 50,000 plates if you have a 4-hour runs. But now if we do quantification, we have some other consideration. Most of the time, especially if you look at clinical study, you're not just interested in running a few samples or bunch of samples. You have relatively large cohort of samples to measure. That means you can really afford to have multiple step separation or 4 hours gradient. So you have also to have methods which are much more efficient, typically a 1 hour gradient. Therefore, you have then to deal with systems which are probably more in the term of peak capacity around 15 or 20,000. So the main problem is in proteomics, and that's true for identification as well, not only for quantification, that you have an undersampling. You have many more things to measure than you can actually measure. And this is illustrated for the identification, where the number of peptides you can actually see in an LCMS run, the actual number of events you trigger, and the actual number of peptides you can properly identify. Right? This is just to give you some figures. And we have a similar problem in quantification, except in identification, usually 1 point or 2 points is enough to get the information. If we will quantify, we actually have to quantify across the entire peak, as we see later on. So we have to have a much higher sampling rate and more data points for each measurement we want to perform. And this slide here is trying to give you the overview of the different strategy you have in proteomics at the present time, right? And what I try to illustrate on this cartoon here is basically here you have different peptides sorted by abundance, the most abundant at the top. And then if you try to measure across many samples, what you have is, because of this undersampling, you may not always collect all data points. And this is the issue in data-dependent acquisition, which have been discussed before. You know, as long as it's important protein, you systematically see the peptide, but as you go to lower abundance, you start having holes in the map. So a couple of years ago, actually it was showed many years ago, but it's now getting a renaissance, data acquisition or data independent acquisition, where you actually scan larger windows, fragment it, and try to get more extensive data set, allows you to fill some of this hole, because you collect a map and you can interrogate against the fragments of each of them. So you get all data points here, but that doesn't mean that the values you get here are actually the actual amount of your peptide, because they are convoluted signals of multiple precursors. So you get the data, but here you have to put a question mark on the quality of your data. So what is usually done for quantification is targeted approach. So the questions here is slightly different. We're not trying to look at the entire proteome, but we try to answer a specific questions. We have, for instance, a set of markers you want to validate in different clinical samples, or you have a biological question, you're following a pathway or a set of proteins, for instance, to measure kinases. So you define precisely what you want to measure, and then you design an experiment according to it, and you measure very specific peptides. So now you will measure each of the peptides you have on list, which here are the blue dots here, and we will systematically now measure it in all samples, because you tell the system, measure it no matter what. There is no decision up front, and you have enough selectivity to get off that. So the real limitation at present time in targeted approach is, because you have also the constraint of sampling, you only can measure a certain number of samples. And the number of samples depends how you set your experiment. You can do small-scale experiment, a dozen up to 100, and now there is a trend to enhance this method to be able at least to measure 1,000 or 1,500. And we'll talk about that later. All right. So the key points we have to follow or address in a quantitative experiment is, first of all, to address the question of the complexity of the samples. We need to have very high selectivity. As already mentioned, a peak is usually composed of several components. You have to be able to discriminate what is the actual peptide from the background of the interference from the matrix. Secondly, sensitivity and dynamic range is a major issue. because the typical proteomics, you have at least 6 orders of magnitude. If you go somebody in fluids, you have even 8 or 10 orders of magnitude with the lowest and the highest concentration. So you need a relatively wide dynamic range, and you need sensitivity because some of the peptides or proteins you want to measure are relatively low concentration. And the last one already alluded for, typically you would try to apply that to larger studies, that means measuring many samples, and in that way you have to have robustness in your sample preparation and also in your acquisition method. You have throughput, so you can measure in a reasonable time frame number of samples. Let's say if you have a 1 hour range that you have 100 samples, it should be doable in a couple of days and not in weeks or months. And on the other hand, what you also want to do is to measure as many peptides as possible in one experiment. So this is basically the challenge you have to address. You want to have sensitivity, selectivity, and you want to be able to scale. That, in other words, means you have to have a relatively fast instrument to work together. And as many things in life, you can have many wishes, but you cannot get all of them fulfilled at the same time. So most of the time, then you will have to compromise on one or the other parameters, depending on what you want to achieve. And then we'll discuss as we move on throughout this presentation. So quantification by mass spectrometer, I'm now going to raise some very basic points. So the first principle is mass spectrometry is a quantitative method. And a couple of years back, I was at another summer school, and I was talking about quantitative proteomics, and Roman Zubarev was in the room and said, what are you talking about? Mass spec is quantitative, so proteomics should be quantitative by default. And this is actually true, but again, there is a few caveats here. So mass spectrometry has a linear response, so what we measure is directly proportional to the amount injected. So this is really the first principle we can enter throughout the quantification. So there's a number of characteristics we want to keep, right? So we would like to have a linear range, so the response is linear, and this is true to a large extent, but it is not true at the edge. So at the lower end, there are issues because we have background, and at the upper ends, we may have saturation. So as we said, we would like to quantify around 6 or 8 orders of magnitude. Best instrument can quantify about 4 or 5 orders of magnitude. There's still a problem at the bottom, at the up. So we have to cope with that. And the issue of that we have multiple signals buried under one main signal is something we addressed. So the second way of doing quantification by mass spectrometry, the second generally used factor is using stable isotope dilution. So this is very old, it's been used for small molecules for 40 or 50 years. So the general idea here is to add in the sample, to your samples, the same molecule you want to analyze, but with a different isotope composition. Right? So some of the carbon, natural carbon and nitrogen are typically replaced by the heavy form carbon-13 or nitrogen-50. In small molecule, most of the isotope labeling is done by deuterium, 2H, which is a problem in proteomics because if you label your peptides with deuterium, they get a different hydrophobicity and they don't coagulate properly, which creates a problem if you want to quantify, because if they don't coagulate, then you have to adjust and correct for that. So this is why nowadays in proteomics, typically carbon-13 and 15 are the method of choice for using stable isotope dilution. Now, quantification, as I just said, in the first approximation, we have the signal which is proportional to the content, and there is a constant which is called the response factor. And that constant is specific to each peptide because not all peptides ionize in the same way. So it is very specific to each analyte, and you have to know that factor if you want to correlate or calculate, knowing the signal, the amount in the sample. So that can be done with the response factor. And each peptide has its own response factor. So, but in practice, this equation is not actually applied all the time because, and this is actually very old stuff I'm talking about. This is really basic analytical chemistry, and all you could read most of the basic and the rules of quantification by mass spectrometry or spectroscopic method in this article here. What you actually measure is the sum of some background. So you have, if you measure a blank, you may still have a signal where you measure. So then you have an offset. So the blank contribution from the blank, then a constant factor times the content, and you have also errors. And this is a major point here. If you do quantification, you should not do just one measurement, but you repeat the measurement, and then you get a deviation and a standard deviation. So that tells you about the errors. And this is not only the measurement. In proteomics, you have to take into account all the steps from the sample preparation, fractionation, etc., up to the final measurement. So, and that can be actually a pretty big factors depending on your sample preparation, also on the concentration of your samples. You get generally pretty good recovery if your sample is relatively high concentration, but if you tend to have very low concentration, all kind of losses happen throughout the way because they stick, or the peptides stick to the wall of the vials on the HP column, etc., etc. So, how do you design a quantitative experiment? That's basically the main questions here. And I think the first thing you have to say, to know is what is the real question, spell out your questions. What are you going to measure in which type of samples? And as we tend to go for targeted experiment, then what you need to define is the number of analytes, that means the number of peptides or the number of proteins you want to measure. So one question is, if we say 100 proteins, how many peptides per protein should I measure? 2, 3. This is one of the questions that need to be addressed. How many samples you want to analyze? If your sample set is, let's say, 5 or 10 samples, you have more time. You could probably even consider doing a few fractions and measure because the instrument time will still be reasonable. If you have to deal with 100 or 200 samples, you would to measure them at least in duplicate. You would not go for a 2-3 hours gradient because you have still to be able to do that in a reasonable time frame. But if you tend to do things over a long period of time, what's going to happen? You have to change columns, you have to change your instrument, and then you get all kind of additional variation you have to cope with during your So this is really questions you need to answer upfront, and it helps designing the quantitative experiment. And then one of the questions is what type of precision or degree of precision do you want to have? Are you looking for small changes, like a 10-20% changes in the modifications where you need to measure very precisely? Or it is a more global screening experiment, you just look like fold changes. Is this protein overexpressed by 2 or 3 or 4 folds in my across samples, right? So depending on how precise you want to measure, you may also use different methods. So very generally speaking, and that goes back to the triangle I showed you before, in essence what you need to do here, performance, so the more precise, the more selective you want to be, go at the expense of scale. So you can actually measure a large number of peptides in a quick and dirty way, if I can say so, or you want to measure very precisely, but then you have to scale down the size of your experiment and measure only a small set of peptides. So then there is a number of other questions you need to figure out before you actually start your experiment. So the first question is, are you doing a relative or an absolute, and I'd say I'll come back to that point later on actually. It's more reasonable to go precise quantification. So in other way, what is your level of precision? That defines the set of experiments you want to do. Are you going to work with stable isotope dilution, either through labeling or internal standard, additional internal standard? Are they available? Can you get access to them? So this is all kind of points you need to consider when you, before actually you design your experiment. And then once you have done this checklist, you then can actually start to plan the experiment, which means what type of sample preparation am I going to do? How do I prepare proteins? How do I digest it? Do I label? Label where? At the protein level, at the peptide level? If I use internal standard, which type of internal standard am I going to use at the peptide level, at the protein level? And then if you have the choice of your instrument, you may select one or other instrument depending on the questions you want to answer. So this is basically what I would like to do throughout the next hour or so, is go through this point and discuss them in some more details and try to address these questions. So the first point is stable isotope dilution. And typically what is done, in most cases, if we do quantification, you have your workflow, you start a sample, you fractionate, or you get your proteins, you digest them, and then here you have your peptides from the digest, and you add the homologs of the peptide you want to quantify in an isotopically labeled form, and you quantify by an LCMS or an LCMS method. And this part is actually pretty well worked out. Reverse-based LCMS works, is reproducible, is quantitative. You get usually data with very precise or relative tight CV. But as already indicated, this tells you about very little what happened here and actually how much was in the samples, right? So this is, if we're talking protein quantification, we need to have some handles on this level here. So there have been different approaches which have been proposed to address that point, which consist in not adding the internal standard at the end, but trying to do it early in the process. So the easiest or the best way would be if you could have the recombinant proteins of the target you are going after and spike it isotopically labeled and spike it in the sample before you do any processing would actually be the best way of doing it, because then if you have losses along the path, your losses would be the same for the protein as for your endogenous protein. And this is actually true, but typically your protein sample might be modified, and the internal standard is typically a recombinant protein without modification. So that would just say it should account for the losses is only partially true, because if you start having selection based on the hydrophobicity or hydrophilicity or the functional group of your proteins, you may still have discrimination here. But that's by far the best way would be if you could label or add the label at the very beginning of the process, and you can account for the different stages. And if you start measuring the losses on the different stage, it is not unusual to have 50% losses, different stages, because some of these stages are quite critical. If you have very hydrophobic proteins, for instance, you could lose them. If you have very small amounts, they tend to get lost as well. So we should not underestimate all the recovery problem across the process. And it is really one of the serious questions if we do protein quantification, is what we're measuring here, how well is it representative of the sample I try to actually characterize. So this is basically the summary slides of what I just said, right? These three levels are at the peptide level, at the first level, and here would be at the very beginning. So this is by far the best way, but as I already mentioned, the sequence of the recombinant protein may not account for possible modification and other things. And doing it at the late stage here is the easiest because the peptides are available, but it does not account for the losses. And you can try to use somewhere in middle of the road. That's the strategy to do that. So this slide from Bernard, in a review, it summarizes the different strategies, and basically here you have from the biological sample down to the data, the different stage. So, and I'm not going to discuss in very much details all the different techniques, but the ones I discussed adding the peptide at the end is the one here, right? If we start doing chemical labeling, there's basically two options. Is to do it at the protein level. So the idea here, you have a control and a disease or treated versus non-treated. You modify your proteins, for instance, as the cysteine residues by using a reagent which is unlabeled in that instance and a label in the second instance. Eventually you label you modify your protein, you characterize your protein, you mix them, and then you process everything in one pot down the stream. So you still have one step here, which is not accounting for potential losses. You have to deal with the chemistry here because you do derivatization. You have to be quantitative with the derivatization. This is an additional step that can be overcome, and you go all the way through. The second way to do chemical derivatization is do it at the peptide level. That means you first digest, so you have one more step. We don't account for the losses. You get your two sets of peptides, heavy and light, you mix them together, and then you measure them together. So you have a control on part of the process. And one way, or the last way of quantifying is not using not internal standard at all. You just use a signal. It's called label-free quantifications, basically just using what I mentioned early on, that the signal is proportional to the amount in the sample. You don't know the response factor. You have to cope with that, and we'll discuss it in a moment. So, but that's basically the different strategy you have on your menu you could select for if you want to design your experiment. And this is things you have to think through at the very beginning, because that defines your strategy. That will define how you have eventually to design your experiment, as well as for the acquisition method, and then subsequently how you're going to process your experiment. And very importantly, in any quantitative experiment, you need to design also your experiment upfront in term, make it statistically meaningful, so you have more than one, right? And then if you start measuring the power of an experiment, you have to take a number of things into consideration. But it is all important points that you do that upfront, because you know to know all the variables in your quantification. It's not sufficient just to measure at the last stage and having a tight CV. You want eventually to measure protein, so you need to account for all the steps in your process. So that basically summarizes what we've seen so far. All right, so the critical factor we have to consider is we need to have a high recovery. We minimize losses throughout the process because we want to quantify and quantify precisely. So that means basically you can't just have a very complex protocol or workflow. You try to get as few steps as possible, because fewer steps means less losses. And fractionation is, in some extent, an issue unless you can really fractionate in a very focused way, so you get all your peptides at the end in the same fraction. If you start splitting it across multiple fractions, quantification really gets difficult because you have to add components from multiple fractions, and that is not a trivial thing. You can overcome it if you have the internal standard inside, but if it's not there, and it really gets tricky if your sample is split across multiple fractions. So this is really the point. High recovery, it's very simple workflow, and eventually you want a method which is robust, so it is really reproducible and not just technical replicates you repeat by the same person in the lab, but eventually you should be able to repeat it over time and even on different platform or different labs. And it sounds very trivial, but it is really not. To have a really robust tested method is actually quite a bit of work. So this basically summarizes everything I said so far regarding internal standard, right? You can put it at different level of your process, and end of the day, you always measure and get numbers. But the sooner or the earlier in the process, the better you will account for the recovery, and the accuracy of your measurement be close to the expected value. Right? Anything else may give you values, but you will have a gap here. And the question is, how well can you estimate that gap? So we have recently tried to address partially that problem by actually trying to get the internal standard, but the same peptide at different levels. So instead of just having one label, one amino acid label, so typically in terms of internal standard, we're working with tryptic peptide. What is done, you label at the C terminus, so the arginine or lysine, and you put all the carbons or the nitrogen or carbon and nitrogen of lysine arginine to N15 and C13. But in addition here, what we did, we added a second label, so second amino acid, second to the last or third to the last, which is a double label, if you will, and you can put it early on in the process, so at least you could try to track the losses through the different stage. And what I try to show you here, this is in a calibrated experiment where we had the endogenous peptide and we tried to map to have ideally the same amount of the first label or the doubled label. You would expect to have them 1 to 1 to 1 if there is no losses. But then you could directly measure the difference in ratio will give you an indicator of the losses throughout the process. And if we apply that systematically, this is now repeating the same experiment multiple times over time, and you look at the ratio, you could see that you have variation, but they're within acceptable confidence interval, and you also have outliers. Actually, here the experiment was done by another operator, so apparently wasn't properly pipetted or something else went wrong, but you can clearly see not only that your experiment is not exactly well, but you can track the outliers. And that, if you start to be quantitative and trying to large number of samples, not only you have to have a method, but you also have to have a QC, because you have to be able to track some proteins which actually, in this case, we add a protein in the sample. It's actually a human sample, and we add a yeast protein with an internal standard, and we track it that across any of the samples, so we have QC, and we know the process is working. Right? And that tells us also some of the losses throughout the different steps. But still doesn't mean it exactly is if you look at one of the specific proteins, but at least you have a control of your process. And I think this is quite important if you do quantifications, not just to do one single measurement. You have to look at the process, and you have to control your process. You have to repeat experiments. You also have to have controls. Anytime you do a series of experiments, you repeat one of the controls part of your new set, and you make sure the controls behaving without some criteria you have defined upfront. Typically, you would accept 10 or 20% variation throughout repeats, and if it's above that, that would put a big question mark. So if we now try to look at the type of experiment we do in proteomics, it's actually very broad and very wide kind of applications. And this is probably now extreme, and I just try to get the two edge, if you will. A classical quantitative experiment, so it means we have a relatively narrow or limited number of peptides, let's say a dozen, a couple of dozens, up to 100 maybe. So it's a relatively limited step, and this falls more in classical clinical chemistry or analytical chemistry, where the point here we want to precisely quantify these peptides, right? And for doing that, we use internal standard. And the internal standard also means it's not only labeled, but it is calibrated. We know exactly how much we add to that. I come to that point later on. So if we go back to the triangle we had at the beginning, here scale is not the issue. What we really want to do is be sensitive, because some of these peptides might be relatively low concentration. And first of all, we want to be selective, because we want to measure. If eventually you think to use such an assay in clinic, you want to have reliable result. So you want to know or make sure that the signal you measure is actually the signal corresponding to the peptide you want to detect, and not some interferences. On the other end, basically it is doing large scale. Eventually we'd like to measure all the peptides, all the proteins in one sample. That may be still a bit futuristic to see it that way in a quantitative experiment with some level of precision. But the point here is the first objective is, can we detect this peptide, and then it's more a relative quantification than an absolute quantification. We may or may not have the internal standard available here, but the main focus here is measuring a large number of candidates in a fairly large number of samples, then multiplexing really becomes the key drivers here. So you can compromise on selectivity with the idea it's a primary screen, you won't see positive versus negative, and then you could always go back and screen with a more precise technique later on, but scale, and to some extent you want to keep the sensitivity. So, you know, this is really what we try to make a proteomic experiment. What is here, it's more classical analytical chemistry. And the last point I'd like to discuss in designing the experiment is now how we're going to measure this or quantify these peptides. And that really now, to some extent, depends on the methodology which has been selected up front. Are we working in a label-free, so we just try to measure the signals and derive some quantitative information from the signal measured? Are we using isotope dilution? And then we have several options here. So we have metabolic labeling, you have chemical labeling, you have enzymatic labeling. All this is, I didn't really go into the details, but I give you the reference. So this is, first of all, what you need to define, which method are you using. All those are basically based on MS1. That means you use the primary signal of the precursor. You can also, because you can increase the selectivity of your measurement, you have two levels of mass selection. You select the precursor, you fragment it, and then you look at one of the fragment ions. You have a much higher selectivity, and we come back to that point later on. And you have strategy which allow you to measure now measuring based on the fragment ions, so the I-track or TNT, where you put a label, and then the label fragments and give you a report ions. So here you use MS2, or typically if we use internal standard, we fragment the energy peptides internal standard. They give you different Y ions because they are labeled, different precursor as well, and this is typically what a targeted experiment by cellular reaction is doing. And also you can start doing also label free, but we don't have internal standards, so rather than measuring on the signal, you measure fragment. That, however, gets a little bit more tricky, but it's also doable. So far what you see, you have a wide variety of techniques from the workflow, how you prepare your samples, where you want to put your labels, if you want to use labels, and then in terms of measurement, you have a number of options how you do your measurement. And that's back to the question I gave at the beginning. What is your questions? What do you want to do? You need to do that and then try to select the best combination of tools you have. Basically, what I'm giving you here is a toolbox, and now depending on what you want to achieve, you have to select the different elements and try to get the best combination there. And the factors you have really to keep now in mind, right, is quantification in MS1, so full scan. Also we can use partial scan, which is select and ion monitoring. We come back to that later on. MSMS, different way of doing that. Then which instrument do you have for doing these experiments? Are they low resolution, high resolution? And we see resolution of the instruments is actually a key factor in terms of defining the selectivity of the measurement. What is the desired sensitivity? What are you measuring? Are you measuring among the most abundant proteins in plasma, or are you trying to measure some cytokine in plasma or some other samples, right? So are you fairly concentrated or very at the edge of the limit of detections? What is the range of proteins you want to measure? Right? And this is back to the first questions: how many samples, how many peptides do I want to measure? Which LC method do I have? I'm using nano LC, which most people are using in proteomics, which is actually very sensitive, but it's not necessarily very robust. People doing clinical assay tends to get to a little bit more robust LC because, as I show you later on, the mass spec is actually pretty well controlled. The instruments are quite robust, but the LC is not necessarily that robust, right? And depends very much on your LC system. So which method in terms of LC, which H3LC system are you using, which type of columns, which type of gradient, are you working with 30-minute gradient, 1 hour, 2 hour gradients, all these parameters need to be considered. So I'm not going to discuss that slide in much details. We can discuss it a little bit more in the workshops. But I try basically to just, and I'm not even claiming these plus are absolute values, are more indicators, just to do some guidance. But this is other kind of factors you need to consider: selectivity, sensitivity, in a mid-range, how difficult it is to design the experiment, how difficult or how easy it is to process the data after you've collected them, and what is the scale, how many analytes can you measure. So this is kind of the checklist you go through, and here are the different methods. Probably you can add a few more, but this is the most common one. So MS1, you basically just collect LC-MS signals and you use a MS1 signal. SIM is not measuring all MS1 signals, but more selectively subset of them, so you get more sensitivity. SRM and PRM, I discuss later on, are targeted method looking at fragment ions, and DIA or TWAS are basically data independent, where you collect all the fragment ions, but they are convoluted. So there is also drawbacks here. So basically the idea here is just to, you see all method has pros and cons, and then before you do your experiment, you should look at that and try to balance and see what is the best options, consider on which instrument you have access to, which sample you have to look into or you want to analyze. Okay, so what I'd like to do now is really go through some very basic of quantification, and this is already showed you before, right? The peptide has a signal which is proportionate to a response factor and the amount in the sample. So the whole discussion of relative versus absolute quantification is actually a very simple discussion, because in general term, if we use internal standard, so this is shown here now, if I use now the unknown is X, and the internal standard, they both have the same response factor, right? And this is the nice things about isotope dilution. You can basically put or get rid of the response factor, and you have the ratio of the signal is equal to the ratio of the amount in the sample of the endogenous peptide, the internal standard. So now if you do relative quantification, you look at the ratio here, which is the ratio of the signal, which means it directly reflects the ratio of content. And this is relative quantification because you can measure the signal of the endogenous peptide and the internal standard, or the heavy and light peptide. And if you do now what is called absolute quantification, and I will come back to the term or the terminology of absolute quantification, basically here you have now the same equation, but in contrast to a relative quantification where you don't know the content of your internal standard or the heavy peptide, for instance. In this case, you know what this amount is, so you can solve the system. So you know, if you know precisely that amount, you know your ratio, you can calculate back the amount of peptide in your sample. So this is basically the discussion about relative and absolute quantifications. Only the discussion do have a good estimate of my amount of the internal standard. Now, the main problem is in proteomics. It's probably more accurate to call it precise quantification than absolute quantification, because the amount of the internal standard, especially if you buy internal standard heavy isotopically labeled peptide, it has a value on the bottle which was basically determined by another method, typically AAA analysis, amino acid analysis. At the time the sample was put in the bottle. But we do know peptides are actually not that stable. They may degrade, they may aggregate, they may stick to the wall. So what was put in the bottle is not necessarily what you can take out a month or week later when you do your action analysis. right? So you can use it as an internal standard, but the amount labeled on the bottle is not necessarily the one unless you repeat a quantification just before doing your experiment. So if you use the same internal standard across your samples, you have a baseline, you can compare it, but I would be cautious in calling it an absolute quantification unless you have rechecked the amount of your internal standard before doing the experiment. So this is the equation in the paper I mentioned early on, right? We still have so far discussed signal as a direct relationship to the concentration, but we haven't really considered the matrix or the background and the experimental errors. And that's what I'd like to try, right? To explain to you. And this is basically so far, if we use this simple equation here, what we do is what we call a single point calibration. We have one point as a reference, and we use a ratio and we calculate back, right? That means, in other words, if we look at the calibration curve, we measure one point as a reference point. It's on the next slide. And we have then basically zero response in the blank, which is not necessarily true. Therefore, if we do quantification according to the textbook of analytical chemistry, what you need to do is a so-called calibration curve where you have your internal standard at different concentration and you measure the signal. And you get a straight line for part of it, that's what is called a linear range, and you see at the edges some special things happen. So what we have done on the previous examples is single point calibration. Basically, we have one point with the internal standard. We assume at 0 it's 0. So basically, in the equation, we just get the proportionality to ignore B, and we do this kind of measurement. And if you measure the signal of the first peptide, you calculate back the concentration and other peptides, so on and so forth. Right? So this is called single point calculation. And it is a good first approximation, but it may not always hold in every case, because at 0 in the blank, and this is very difficult to get a real blank in proteomics, right? If you measure pesticide or caffeine in your coke, it's always possible to have water or another sample without the analyte inside, and that we consider blank, and we could see if there is a signal in your blank. In proteomics, it's very difficult to get samples without the proteins of interest you're trying to measure. So this is not that easy to measure a blank and measure. But in most cases, if you measure blank, and measure blank is usually, especially in proteomics on clinical samples, it's not just measuring one sample, you have to measure at least a few of them, because most of the controls will still differ from case to case. So, but at 0, the signal will not be 0. So you have to deal with at least an equation where you have an offset. So, in other words, if you have backgrounds, you see that now your curve is no longer the yellow curve. If you do the Lynch curve, you would see the blue curve. So if you use a calibration, a linear line, you have to use this equation there. And if you're close to your single point, the errors might not be that big, but if you go too far away, you see that you can have significant differences. Therefore, having a calibration curve in the right matrix is actually a quite important factor. So this is now, again, all the points you want to consider. If you try to quantify precisely, measure, right, came to the point, you can measure very precisely. Can you measure very accurately? This really depends on your internal standard. You want to measure, and this is basically textbook of FDAs and others if you want try to really make a quantitative method. This is not the full list, but it's a key point of what you need to address. The method has to be repeatable and reproducible. Repeatable means you can repeat it by the same experimental and same instrument and get the same result, which is not that difficult. Reproducing is maybe repeating the same experiment from A to Z on a different platform, or the same platform but in a different lab, but a different operator. And that is not always that trivial. It seems trivial, but it's not. You want to be specific, you want to know the limit of detections, lower end, upper ends, and quantification of your method, and basically doing the dilution curve I showed you before, and you want to make sure you have a range where it is linear. So in other words, you have your method here, you will define a limit, which is the lower limit of detection, and there are different ways of defining it, but the simplest way is you have signal to noise larger than 3, that is your limit of detection, and you see this is where your linear range stops, because the background's taking over, and what is limit of quantification is basically 3 times the limit of detection, or signal to noise 10, that's where you can properly quantify. And that means if you can detect signal to noise 3 or 4 to 1, you could see probably my peptide is there, but it would be not judicious to quantify, try to quantify, because you're not in the range you can properly quantify. And then you have the linear range where you quantify. And if you go to the top here, what happens? You add more samples or more analyte in your sample, but your signal doesn't grow anymore, or doesn't grow in a linear way anymore, because you're in the saturation range. And that happens in most mass spectrometers, right? You have about 3 or 4 orders of magnitude here. Here you're limited by the background, and if you add more, usually you saturate your system, and you can no longer quantify. So this is the things or the characteristic of your system you need to know if you want to properly quantify. So I'm not going to spend too much time on the signal to noise, but the easiest way in practice to do signal to noise, if you measure a peak, you have the baseline at the left and the right of the peak, and you see it's fluctuating, so that gives you variations that we could call it the noise. You can measure the signal and you can measure the ratio. So that would be, with the old chart recorders, was the easiest way to measure, because you could measure your signal, calculate signal to noise. With modern system, actually the informatic in the system tend to smooth out the noise. So it usually looks much less noisy than it actually is, and it is really not that easy to measure signal to noise. And the signals usually looks much better than it actually is, and you overestimate your limit or detection and quantification. So the basic, if you could do that, if you have a factor 3 here, you can properly detect, you can confidently say my peptide is here. If it's 10 to 1, you can start quantifying. If it's not 10 to 1, you should not quantify, because you're not in the range you can properly quantify. So there is a statistical approach, and again, this is part of the article. I give you the reference, and I can quote the article. It describes you from a statistical point of view. If you measure your blank and then your samples, you always will have, typically we say 5% here, 95% confidence. You have a range where you have false positive or false negative, so that would be your limit of detection, but you want to quantify in a range where you're actually pretty confident that you have very little interferences. And if you want more details on that, you can go back to the article. And to the last point, you remember, and I show you the equation, you had A plus B times the concentration plus an epsilon, the errors. It's now, try just to show that on this cartoon here, is that actually each measurement, you repeat it over time, you get an average and a standard deviation, right? So each measurement has an error and a standard deviation, and you need to repeat the experiment to have a handle and know how much this is, and then eventually your calibration curve is not necessarily just a straight curve, it has confidence intervals, these all mathematics have been worked out. If you have your curve and your different points, you can also measure the confidence interval, and it tends to be larger at lower concentration because the noise is just higher. All right, so one of the important factors is selectivity of the measurement. And already, as I showed on the first slide, typically what we would measure in an instrument is one signal, and if you have a complex mixture and your chromatography is not good enough and you separate all the different individual constituents, what you'll have is actually a signal observed, which is a composite of your analyte of interest plus interference or interferences from co-eluting species. And proteomics, typically, all the peptides are eluting at a given hydrophobicity, and they also tend to have very similar masses. So the first thing you can do is go to a better instrument, try to resolve them, and that is Now with high resolution instrument, 50, 100,000, 700 of 1,000, you can properly resolve your different precursor, and then you can now, if you do quantification based on the precursor, isolate the different components, and now you do a much better job if you look, because you can separate the peptide of interest from the matrix interferences, right? So better resolutions allow to do that. The other way to go around it is using tandem mass spectrometry, not quantifying on the precursor, but quantifying on fragment ions. So this is to link to the previous modules, right? Actually, what if we quantify the value I measure here may not be the true value, because the true value is actually would be here if I could properly separate, right? So that shows you that what you measure here depends very much on your selectivity. Or in other words, only if you have a very selective system, you can trust the value you measure. Otherwise, you have to be very careful, because often you would overestimate your peptides because of the contribution. And this is one of the examples. This is one peptide at a typical resolution, pure exactive data, so this is a nominal resolution. But you see here, the actual peptide you want to quantify is this small shoulder here, and it is very difficult because you have another peptide here. It would not be possible to properly quantify because they overlap. If you increase the resolution, double it, you can actually properly now separate the peptide from the peptide of interest from the contribution, and you see that by having better selectivity, if you do the dilution curve, you see that you can get now to reasonably good sensitivity, because you have very good selectivity. So this is one example to try to illustrate the point that often if you're not careful, you may take that peak and take it as granted, and you measure this as a whole, but actually what is your analyte of interest is the shoulders here and the small thing here, right? And if you're just using a low resolution system, you may just want to see that. And that's actually quite common that these things happen. And if you go in literature, quite a number of data, quantitative data, can be questions because the selectivity of the system was probably not appropriate. So if you don't have enough resolution on the MS1 to separate them, what you can do is actually use MSMX, because that's what I represent here. I'm assuming that this is the precursor ions, and the precursor ions is not one species, but it's actually this here, as I showed you in the previous slide, is a composite of these two components. If you now fragment, you'll get the fragment ions actually of both precursors you isolate and fragment. But the fragment ion will be discrete, and they will, with very high probability, give you different masses. So now if I use, for instance, this and this fragment ion in the MSMS spectra for the quantification, I have the selectivity because it's free of interferences for the co-emitting species, right? So one way to do quantifications and increase selectivity is measured in or at the MS2 level, where you select the precursor and then you look at very specific fragment ions. Right? And this is just a couple of examples to illustrate that. This is part of an LCMS run. At the same, we try to look at this peptide here and looking at two fragment ions. So this is a precursor 504.3, which is selected in the first analyzer. I shall come to the measuring technique in a minute. And you look at the fragment ion 793.4. You see here it's unique. There is another one later on. But if you look at this one here, the 504 to 515, you may, if you're not very careful, pick up these ions as the right one, which is actually not, and this one is here. And if you look at the spectra, this is actually the wrong structure, the wrong peptide, even it has the right precursor, and this one is actually the one you want to quantify with these two fragment ions. Right? So it means if you just look at fragment ions, you have to be careful, because if you have complex mixtures, you still have, for very specific selection of what we call transition pairs of precursor and fragment ions, multiple stigma which can happen. And this is even more true If you look at low concentration, this is just one peptide spike in a digest, and you look at specific ions, here the 959 and 789, you see that for one given precursor, if you monitor that across a reasonable short range, actually, you get many hits, right? So even we have two levels of selectivity here. This is done with triple quadrupole, so low resolution mass analyzer on the fragment ions. You get multiple options, and you have to be careful because your selectivity is much better, but still not unique. So that's the message so far, right? Selectivity really becomes, or background and interground really becomes an issue once you have very complex samples, because what you think, even precursor selection followed by product ion selections, is not that selective as you see on these examples. So what I'd like to do now for the last segment is how we actually do now a targeted experiment. I showed you all the questions you have to address. I showed you the issue to design the experiment, how you quantify, how you need to have internal standard, and the main question is how to get enough selectivity. So how do you do a targeted experiment? So as I already mentioned, you start with the questions. You have a set of proteins you're interested in. Now, from this set of proteins, we're doing shotgun, so you can measure all peptides. You select a few representative peptides of these proteins. And you have to deal with the inference problems being discussed yesterday by John. I'll come back to that in a minute. But that defines you basically the set of peptides you want to measure. Once you have to done that, what you need to do is create a method, because you have to drive your instrument. Right? If you do shotgun, basically you have a sample, you inject your sample, goes through the H-base separation, and the instrument basically is on autopilot. It decides what to measure, it triggers the MSMS events. Here what we do, we actually drive the instrument and tell them exactly what to do at each point in time. So basically the main point of a targeted experiment is to design the method, select the right parameters which allows you to do the targeted acquisition. And that can be done on a triple quadrupole instrument or some other instrument, as we see later on. I already addressed the question of the sample preparation, right? You have your high recovery, you have your interim stand, all that has been solved. So basically you now collect your data, and what you want to do, you get the data, and you have to do two things. The primary goal is to quantify, and what you do here, you monitor your peptides across a window when it's eluting, and the two colors here represent your peptide in the sample and your internal standard, and then you can just quantify based on the area under the curve. Now, as I showed you in the previous examples, right, like here or here, right, you still have to be very careful to make sure what you measure is your right peptide. It's not some other species which has the same ions at the same places, but might not be the right peptide. So this is quite important part and often neglected in proteomics. It's small molecules been known for 20 years and very specific rules how you quantify and what additional measurement you have to do to confirm identity. But this is an important point here, that you not only want to get the trace and quantify, you want to have enough or additional information to make sure you have a fingerprint and you measure or you quantify the right peptide. So how do we design the experiment? So we have the proteins, we select a few peptides for each of the proteins, and then the easiest way to design the experiment, you have in one way or another access to the MSMS spectra. Now, how do you have access to the MSMS spectra? There are different options here. Nowadays, there are more and more libraries. You could just go on the internet and access to this library. You put the sequence, you get an MSMS spectra. Or you have done a discovery experiment in your lab. You have collected all this MSMS data. You have the peptides. You can go back and just now look at the MSMS spectra, which ions are suited for an MSMS experiment. And still you want to quantify the general rules, and I'll discuss it a little bit later on the next slide, but basically you would take 3 ions, most intense and as possible selective. So we come to discuss that. And basically the experiment you want to know, to design is basically
and we'll see that as we look at the instrument, but you need to define the precursor, so the mass of the peptide, the mass of the fragment you want to measure, and a few additional parameters, which are when the peptide is eluting and how long you want to measure it. Once you do the experiment, you collect the data, you eventually have to process all that data. We'll discuss that in more details later on. But for the first point, the selection of the peptide. And there are a few simple rules here. And basically that addresses two issues. The first one is the uniqueness of the sequence. It has to do with the protein's inference, because you want to make sure your peptide reflects the proteins you're looking for, at least the class of proteins. Sometimes you have isoforms, so you may just look at the isoform family rather than the individual isoform, but you don't want to have a peptide which is common to 5 or 6 proteins, because then you measure something but you don't know what you measure. The second thing, not all peptides behave equally well in chromatography. Either they're hydrophilic, they come to only on the column, or hydrophobic, they never come out, or very late, or very broad peaks. And in terms of mass spec, not all of them ionize equally well. This is the point we discussed earlier on with the response factor. Right? So each peptide has its own response factor, but you tend to want peptides which have good response factor, they respond well. Otherwise, you may walk into problems. And one of the classical problems is in quantification. For instance, a lot of people are interested in phosphorylated peptide, but the fact you had a phosphate group on a peptide typically decrease the response factor by a factor 10, right? So there's just some groups or some constituent of a peptide that makes them not as good, what we call flyers. They don't ionize very well, or they're not as good. So you tend not to select that in a first pass. Now, if your question is to measure a very specific modification or a very specific peptide, you may have less choices. But if you design a priori a method, generally you tend to select the best peptide in terms of ionization. And also, they have to fragment quite well. Not all peptides fragment equally well. And here it is not necessarily because it is a good peptide for identification, it is a good peptide for quantification, because some of the peptides which give poor identification because they have very few fragments, so they usually have very poor mass spot score or the database search score, they're actually quite good in terms of quantification because the signal is concentrated in few fragments, so they have much better response in SMS. And there are a couple of examples of that, where actually for quantification, you may just select a peptide which have few fragments, that is very specific. And last but not least, and that's addressing all the points I have discussed earlier in the workflow, you have to make sure that your peptide is representative of your product. So it judges quantitatively, so you don't have too many missed or miscleavages, and that your peptide is stable, because if it further degrades, then you have multiple components representing your peptides, and then the quantification is going to be biased. Now, the more difficult question is how many peptides per protein do you need? There is no universal answer to that. Typically, I would say you may want to have 2 or 3, and if you want to try to be representative of your proteins, you want to get some at the N terminus, some of the C terminus, and maybe some in the middle, so you at least know if they correlate. You have measured your full-length proteins, but then if you, and that's another discussion we can have later on, if you look at correlation between peptides and one protein, often you have poor correlation, and that means a number of things. One of which that you not necessarily have the full-length protein in your sample, you have a mix of different isoforms. So this is actually then inferring peptide to the protein is a challenge, but that having exactly the same response and makes sense out of deviation for a non-correlation is actually quite a bit of challenge in some cases. So this is just to illustrate the point I made, right? You look at the peptide, so you want typically peptides which are unique, they correlate to one proteins. So this is in green as the peptides, in blue the proteins. So like a peptide which points to many proteins as the ones you want to exclude. So you have to do that exercise first when you design the experiment, select properly your peptide to be quantitative, but not only quantitative, really go back to the proteins of the information. So I think I summarized so far most of the points, right? We targeted, we try to overcome some of the limit of regular shotgun experiment by now really looking at what we're interested in, and we want to be quantitative, and we have to fulfill a number of factors. So how do we do that practically is the most commonly used technique has been now for a decade or so, triple quadrupole instrument. So the experiment is that one I showed you data already. So the way you do the experiment is using a triple quadrupole. If we do triptych peptide, typically we select doubly charged peptide here. The fragment, the undergo fragmentation is the collision cell, and the second analyzer, which is also a quadrupole here, is used to select one specific fragment. And you can then sequentially measure different fragments, and you have to measure, I would say, 3 or 4 fragments to have some level of selectivity. I showed you on the example before, one single fragment would not be selective enough. So typically 3 or 4 fragments, and you measure them sequentially, so you build a loop, and you measure them across the entire chromatographic peak. And in essence, once you have designed your method, the data you get are very straightforward. There's this ion chromatogram. Quantification happens just by quantifying the area under the curve. And if you do isotope dilution, what you will do, then you repeat the measurement on the same peptide, now isotopically label the corresponding fragments, and then you do the quantification using the ratio of the isotopically labeled peptide versus the endogenous peptide. So here you have the 2 levels of mass selection, give you the selectivity. You have sensitivity because here you're no longer scanning, so you can sit as long as you want. Typically we're talking 10, 20, 50 milliseconds here, and you can stay longer if we wish to, and you can measure this ion for one more time, right? If you would do a, let's say, 1 second scan at mass from 400 to 1400, you would only measure for 1 millisecond. So you have basically a 2-fold increment in terms of sensitivity using a static measurement versus a scanning device. And at present, triple quadrupole have really the widest dynamic range. If you stretch it to both ends, low and up, and you get up to 5 orders of magnitude, 4 easily, sometimes a bit more. In terms of time, I'm not going to spend much time on how we select the collision energy, but fragmentation is very much depending how much collision you put. But the good news is here, if you look at Y fragments, which are dominating in the fragmentation of triptych peptide, they have a relatively broad range, and if you're not too much off, couple of minutes, plus minus 5 vol, you still hit the top of the peak, and you're pretty good in the selection and the fragmentation. Some other ions, such as the proline cleavages or B ions, tend to have lower collision energy. So the default value from an identification might not always be the right one, but it is often for the first type of experiment close enough to use that as a default value. How do you select the fragment ions? So there's basically 2 simple rules, and this is a spectra, so this is the precursor. So you want to be sensitive, so you tend to see the largest ions because they have most ion current. And you want to be selective, so you see here, if you look at the noise, you have more noise to the low end of the spectrum. So you tend to take the ions with the sequence at the upper end. There's all monocharged, singly charged ions here. So basically the rule says the highest ions above the precursor. Right? And you make sure that the fragment ions have different masses if they are labeled. This is the endogenous peptide, the isotopically labeled. They have discrete masses, so you don't have crosstalk across the channels. Otherwise, you may have also ambiguities if your resolution is not sufficient between the precursor. But if you really make sure your fragment ions have, if you take Y ions for peptide which are labeled at the C terminus, it's always the case. It is not true if it's a B ion, because the B ions on such a peptide would have the same masses regardless if they come from the precursor or the peptide, the interstitial, or the precursor of the interstitial versus the endogenous peptide. And then once you have that, you can do dilution curve and do everything we discussed early on, and you can then properly quantify at interest of time and moving a bit faster here. But this is basically summarize a triple quadruple experiment. You select your peptide, you fragment your peptide, you get the traces, you use the traces for quantifications, and here you have the method. So I discussed the collision energy, how you set it. Now what you also want to do, if you try to scale the experiment, is not measure all the peptides all the time. You know where they're going to elute, so you set very defined windows where you predict the elution. That's why we put the elution time here as a constraint. We only measure the peptide where they're going to elute. That's something we can discuss later on in the workshop. The second point here is, back to confirming the identity, is if you have a number of traces, you can reconstruct a spectrum or a radio spectrum and use the erratic ion abundance here and make sure these ratios are right or this pattern is right to make sure that your peptide is indeed the right. So what I'd like to do now is SRM on triple quadruple is widely used and very useful and gives a lot of quantitative data. However, it also has some limitations. The first one we've discussed already here. We have a low resolution quadrupole for the mass selection. Even we use a 1 Dalton isolation window for the precursor. We have also the fragment ions which can coelute, as I showed you examples. So this problem still is a problem we need to address. The second problem is now the quantification and the number of events. And that brings me to one of the last basic points we need to discuss. If you want to quantify properly, according to the textbook, you have a chromatographic peak like this one here. You need to have about 8 data points across the peak. So in other words, if you're running a standard column and your peak is about 20 seconds, you want the distance between the peak here to have enough points, about 2 seconds. Right? That basically defines the cycle time. And now you have to synchronize your mass spectrometers and the number of SRM events you want to measure to fit here. So if you say I have 2 seconds and I use 100 milliseconds for each ion, that means you can measure 20 events, right? 20 events means 4 ions for 1 peptide, and have the corresponding isotope labeled peptides, that means already 8 events. So you could measure at most 3 or 4 peptides and have a reasonable duty cycle. So you have a limitations here in keeping the duty cycle and the number of peptide or transitions you want to measure. And this is really part of the challenge, and that is from the example I showed you before with a triangle where you have the experiment, you do quantification of smaller sets. If you only have a small set of peptides, you can easily do it because you usually have less than 3 or 4 peptides within an elution window. But if you're going large scale, you have many of them and you have to cope with that problems here. Keep the duty cycle and increase the number of events. So that's why the second generation of targeted experiment in which we're using orbit trap instrument have become handy in that the aim here is to do everything on the benefits of a SRM experiment. So that means we systematically measure all the target we want. Right? That was one of the first criteria we said. We want to be systematic and measure the peptide across all samples systematically, because this is one of the main problems in quantitative proteomics. If you start having missing value, you have problems in terms of analyzing the data. So we have systematic measurement. We can be quite sensitive. However, we have the coalition of co-isolation of species due to the low resolution. So if we have high resolution mass analyzer, we can overcome some of these problems. So we can have much better selectivity. As I show you later on, we always collect all the MSMS fragments, not only a few of them. So this helps for the identification, but also helps overall with the experiment. We can be sensitive because we have trapping device. This I am not going to discuss this morning because it's not enough time to do that, but if you can trap, there are very few ions you can trap for quite a long period of time, and you can detect with very low sensitivity in the subatomol typically. And we can multiplex if we have large scale experiments. So this is a cartoon try to represent. In essence, what it shows here, that the front end is basically the same as a triple quadrupole instrument. What is changed here, we replace the second quadrupole by a high resolution mass analyzer. In this instance, an Orbitrap. In principle, you could put a time of flight or some other high resolution mass analyzer here. And the difference here now, you select the precursor, you generate fragments, and all fragments are collected simultaneously, so you get a full MSMS spectrum. The difference here between a targeted high resolution experiment and a DDA experiment, we're not only collecting a few times and then move on, we'll collect the MSMS spectra across the peak every 2 seconds to have a proper data set to be able to properly quantify. But what happens here, we collect all the data and subsequently we will process the data, extract the traces and quantify. So it's basically what is here. The benefits of doing that experiment is in terms of experiment design, it's much simpler. I don't have to decide which fragments I'm going to select now. Basically, you just say which peptides are going to measure, you know M over Z, and you can guess what the elution time. So the experiment design is pretty straightforward compared to a targeted triple quadrupole experiment. You have full MSMS spectra, so it helps for identification because you can then make sure first you have the right peptides, and then you can select the fragments you want. And the processing is decoupled from the acquisition. You have much more flexibility selecting the ions, do iteration. If some ions for some reason are not convenient, they have interference, you can go back and re-extract different traces. On a triple quadrupole instrument, you design your experiment, you collect the data, and for some reason you say the second transition is not good, it's too much interference. You have to go back, redesign the method, re-query the data. So it's a lot of overhead if you don't iteration. So this basically compares the two methods. The difference here, we collect the transition one by one sequentially. Here we collect all of them at once. That's also why we call it parallel reaction monitoring, and this is sequential serial acquisition. So the entire workflow, how the data, and I probably will stop focus on this one and skip some of the subsequent slides. So the actual experiments performed on an Orbitrap instrument where it's a little bit more complex than the one I showed you before. You basically have a seed trap, the collision cell here, you create the fragments, ions here, and eventually the fragment can be put back into the Orbitrap where you collect full MSMS spectrum. You have a trapping device here. In principle, you can multiplex measure multiple precursors, fragment them, and then measure them collectively. Especially if you do quantification, what you can do is collect, first of all, the endogenous peptides, second is the internal standard, get all the fragments, move them, and measure them collectively. Then you get the full MSMS spectra. You can first look that you have the right peptide, and only if you have the right peptide, you start extracting the traces and do the quantification. So it's a change in paradigm here in that you first do the identification or confirm the identity, and then you quantify. The important point here, especially if we do quantification and we do it systematically with internal standard, we build a library with the internal standard under the same conditions, and this is a quite important point, and we can really make a match here, and if the match is good, we know we have the right peptide. Also, this library is very useful then to select the precursor and do the extraction. So this is a bit more details, interest of time, and skip that part. And this is basically summarize what I said before now. The method here, you have to do much less work up front because the only things you select your peptide, the mass of the peptide is not that difficult to predict. It's M over Z, typically doubly charged, sometimes triply charged, and you need an estimation of the emission time, so you could record them as a prototype. And that's really now, if we compare here, we can get much more dense population with very little interferences compared to an SRM, because here we have the second level of selectivity, which is not only a second level, but it's a high resolution second level, so we can really discriminate the interferences from the background. And I'll show you a few examples to illustrate that. This is the SRM data. The interstandard is pretty okay, but if you look at the actual peptide, which is in lower concentration, this is really data you shouldn't even consider trying to integrate because it's basically noise. If you look at PRM mode with higher resolution, you can really extract very narrow windows. You have very nice signal for the peptide you try to quantify as well of the interstandard. If you look at the ion ratio, they also correlate very, very well. And this, if you apply it, I'm not going into the details in the interest of time, but there's an SRM data set. You see control and disease. You clearly see a higher expression if you quantify. But if you look at the response factor of the different peptides, they're kind of similar here. But if you look here, there's clearly a discrepancy. That put you a red flag. If you look now here in high resolution mode, they both peptides respond equally well, and there is no discrepancies anymore. And this clearly tells you, in that case here, you have interferences which contributes to that signal here. Right? And you can see plenty of data in the literature like that, but once you have done the corresponding high resolution experiment, you can question how much this data are reliable, because you clearly see this is not, it is quantitative data, yes, but it is not selective at all, as you can see from that. So how do you control the selectivity? Again, I'm running at the end and not going in detail. So you get much better selectivity if you get higher resolution here, but also the window which you use for the selection of the precursor is important, because the larger the window, the more peptide you're going to co-isolate. This is published, you can read it in more details, but basically it shows a map. You open the windows and you look at the different resolution. So, and this is not the highest selection we done. We can now done 1 Dalton, half Dalton, haven't that on that slide. But you see here, if you take a typically 1.5 Daltons, even at 70,000 resolution, you get, and this is a large-scale experiment, about 5% of your high-resolution data are still interfered or not selective enough. And you can try to address that problem. But as soon as you relax either the resolution of your second analyzer or you use larger acquisition window, and that open question mark for the IA swap experiment, you see that the number of interferons go up very drastically. And if you're really very relaxed criteria or parameters, you get easily 20–30% of your peaks or your signals which are interfered. So I think that summarizes the different steps, right? So if we do PRM, so the front end is the same. You select your peptide. The acquisition is straightforward. You have to define the instrument parameters. I just show you a few points how you select them. I cannot go into the details here, but basically the resolution, the field times, the key parameters. And in terms of data processing, you do it post-run. You also shift the paradigm in that you first make sure you have the right peptide, you have the full MSMS spectra, you can even see interferences, and then you quantify using the proper traces with extraction. You use actually very tight 10–15 ppm windows, and you get very selective signal, very precise quantification I showed you before. And this is all possible using existing tool. You don't have to design special tool. We have been working with Skyline to basically have the interface. So you do the method as you would on triple quadrupole, and then you can apply it, and the data are then collected and translated and processed. So what I'd like to do is try to fix that magic, but I'll probably do it more in the workshop, how we compare these things. So we can go through the different methods and compare them, but at interest of time, I'll skip that. The pros and cons for each of the methods, but we can look at that offline. Want to do now is quickly go to 2 more things, and there are 2 minutes left, so it's 1 minute per slide. So this point I kind of addressed already. So it's the scheduling. You need to get reasonable cycle time, duty cycles. and match the number of events. And the only way you can do that is instead of measuring peptides over long windows, you can measure them very short windows where you schedule them. And chromatography, as I said before, is actually the most tricky part, and you always have drift. So what is now possible with the latest, and there is a paper out describing that, you have a few peptides which you put into your sample, which we call landmarks, and you record them on the fly. You know with the system you can define, make sure you have the right peptide. And if there is a drift in elution time, the system can correct for that. So this is basically on-the-fly corrections. You monitor some peptides, you know them in your sample, and if there are drift, you competence. That allows you to monitor your peptides in shorter windows. Typically, you would put 3 to 4 minutes. Make sure you get your peptide. If you have the dynamic correction, you can handle 1 minute or 1.5 minutes. So that means if you have 60-minute gradients, you can do 60 segments, let's say with 10 or 15 peptides. So you see 60 times 15 gives you roughly 1,000 peptides. That's what you could measure if you can really control your elution times and control your chromatography. And as I said before, in this large-scale experiment, the challenge is less the mass specs than actually getting a good chromatography and controlling your chromatography. So if you now look at that typical data, and this is now obtained on Q-Exactive, is basically the resolution of your system defines the transient time, and if you want to be very efficient, what you do is trapping at the same rate as you measure it. So while the trap is trapping, the Orbitrap is measuring the previous scan, and then you load and go so and so forth. So if you have a long trapping and transient, you have high resolution, you have high sensitivity, but you're limited in the number of peptides you can measure in one cycle. If you decrease, you get shorter time, you lose sensitivity, you lose resolution, but you get many more peptides, right? And this is the whole dilemma for Fonro scale. So here you have perfect data for quantification. Here you can detect, but if you apply the rule signal to noise 1 to 3 or 1 to 10 to quantify, you cannot quantify poor ion statistics because you don't collect enough ions. So can we collect or try to unify the two worlds, try to have scale and performance at the same time, and that's something we recently showed. Basically, using what we had previously showed, that you could control the chromatography, that is here actually changing the way you do the experiment. And rather than monitoring the endogenous peptide and then subsequently using the internal stamp to quantify, what we do here, basically we have two acquisition modes. Right here we have something fast and we can measure a lot, quick and dirty. So that's what we call the watch mode. And then you can switch to a mode in higher resolutions, or relative, right? Higher resolution, longer time, more sensitivity, and you can properly quantify. So the idea here is to use two different acquisition modes, and the other idea is use the internal standard. So if we do quantification, we know we add the internal standard in samples. So because in a sample, you're doing a large-scale experiment. Sometimes your peptide may be there, sometimes not. So if you're watching it, you're not detecting it, you never know. Did I miss it? Was it other? Was it below limit of detection? But if I have the internal standard or a level I know I can measure, detect, and quantify, I first monitor in the watch mode, low resolution fast, and if I can detect, the system will then switch, and this is using the fact that we have a library. We can make sure we detect the right peptide, we switch to a high resolution mode where we can properly quantify. This is illustrated on this slide here. So this is here, we monitor the internal standard. You see we can, from the time we start looking at it, we see the peak. Or this is, no, excuse me, in blue is a reference from the library. So here we start seeing a few spikes, but they're still not, right, a good match. We get more ions here, it's better. At some point we get enough signals around here. So this is a perfect match. The system will now switch to quantify mode, which is shown on the next slide. So high resolution, longer time, better signal to noise, better quality data. And at the same time now you measure the peptide, which is the non-labeled form, and you can then properly quantify it. So kind of reaching the end, so I tried to summarize here. So all this, we can discuss it later in the workshop and has been published in a recent paper on the MCP if you want to have more details here. But I hope there was quite a bit of material here, but I could show you that we can quantify by mass spectrometry. It is a quantitative method. Best way to quantify whenever possible is to use internal standard. We have to be careful what we want to do. Absolute quantification, I think it's still very questionable because it depends very, very much on the quality of the internal standards, purity, azote purity. It's probably more judicious to call it precise quantification versus relative quantification because this is really a question of the internal standard. All quantification is basically a question of designing the experiment. What is your questions? What will be your strategy? And you have to do it from the beginning. Design the experiment, the number of samples you want to measure, control, disease, which sample preparation, label, not label, get the right internal standard, choose the right instrument, the right acquisition mode, try to answer best your questions. And as I showed you throughout the presentation, the question you always want to address is which level of analytical precision you want to reach in terms of selectivity, precision of your measurement. You have to replicate your measurements. You need to know the variance at the different levels. And an important point, always try when you can to figure out what is the noise in your experiment, because signal to noise tell you if you can actually detect or even you're allowed to quantify, right? And it's often overview. And end of the day, it's all about data quality, and design is a proper experiment eventually will give you data with high quality. And hope I wasn't too long. I'll stop here. I'm happy to take any questions.